the largest glacier on Earth, is systematically breaking the rules of the calendar. For decades, the structural dynamics of the Antarctic ice sheet were assessed in increments of centuries. Today, the leading specialists monitoring the system have abandoned that temporal scale. The documentation now uses immediate markers, this year, or any day now. At the absolute edge of the continent, a floating slab of ice known as the Thwaites Eastern Ice Shelf is fracturing, pulling away, and entering the terminal phase of structural failure. It is a natural barrier behaving exactly like a concrete dam under structural overload, where a widening crack has propagated entirely through the retaining wall. The analytical question has shifted from whether the barrier fails to the precise mechanics of the moment it lets go. This is the frontier of the Thwaites Glacier, an architectural anomaly that researchers call the Doomsday Glacier. It is the widest glacial body on Earth, presenting a continuous marine front that stretches roughly 120 kilometers across, a scale equivalent to the entire width of Great Britain or the state of Florida. Vertical measurements reveal a solid wall of ice close to 2 kilometers thick, extending more than a mile from its bedrock base to its upper surface. The floating shelf currently bracing a sector of this massive system is a slab approximately 350 meters thick, extending out over the open ocean. In the strict physics of glacial retention, this shelf functions as a mechanical cork or a structural buttress, exerting a continuous counterpressure that limits the velocity at which the grounded inland ice mass slides towards the marine basin. The immediate crisis is defined by a severe structural deficit. This entire floating shelf, responsible for holding back an upstream ice mass more than 5 times its own thickness, is pinned to the planet by a single point. At this specific geographic coordinate, a submarine ridge rises from the seafloor, acting as a lone mechanical anchor where the underside of the ice sheet catches against the rock like a fingernail hooked on a narrow ledge. A load the size of an entire country is resting on a single underwater contact point. The empirical proof of imminent failure is not a speculative model. It is the result of direct measurement. A comprehensive study published in 2025 compiled a rigorous 20-year dataset spanning from 2002 to 2022. Integrating satellite observations, precise ice flow speed metrics, and GPS instruments anchored directly into the ice surface. This 2-decade time-lapse captured the systematic degradation of the shelf's shear zone, the highly stressed boundary seam where the moving ice shelf grinds against slower ice and rock features at its flank. For 20 years, mechanical stress has concentrated directly within this critical seam. The fractures have grown continuously, systematically erasing the structural integrity of the zone and loosening the shelf's grip on its single submarine pinning point. The surface and the marine underside are now heavily laced with interconnected cracks, signaling a visible detachment from the main grounded glacier. The data has forced leading geophysicists, including representatives of the British Antarctic Survey, to project the total breakup of the shelf within an immediate window, potentially as early as 2026. This imminent collapse introduces a profound physical paradox that misleads casual observers. Because the ice shelf is already floating, it displaces its own weight in water. Its immediate shattering will not raise the global sea level by a single inch on the day it occurs. The floating ice cubes melting in a glass do not cause the liquid to overflow. The true systemic threat lies entirely behind the shelf. The main body of the Thwaites Glacier is grounded on solid land, resting inside a deep geological basin that plunges well below sea level. The floating shelf is not the source of the water. It is the brake system holding back a continental deluge. Once this mechanical constraint is removed, the grounded inland ice is clear to accelerate its descent into the ocean. Oceanographic data reveals that this structural unbuckling triggers a process scientists classify as a largely committed sea level rise, a chain reaction that will continuously unfold across centuries even if atmospheric warming could be instantly halved. The root cause of this structural failure is hidden entirely from view, operating deep beneath the surface where the atmosphere cannot reach. The southern ocean surrounding West Antarctica is stratified into distinct thermal layers. Far below the freezing surface water, a massive current of relatively warm, dense, salty water travels continuously along the seafloor. Because the base of the Thwaites Glacier lies in a deep submarine basin, this deep oceanic heat is driven directly inland, penetrating beneath the ice shelf and striking the exact zone where the ice anchors to the Earth. The single pinning point is not being melted by warm air from above. It is being aggressively dissolved from below at the precise structural junction where the ice sheet grips the submarine ridge. This localized destruction is the direct expression of a planetary scale imbalance. The global oceans cover more than 70% of the Earth's surface, and they have absorbed approximately 90% of the excess heat energy trapped within the Earth system by greenhouse gases. That immense thermal energy reserve is circulating through the deep marine architecture, and a critical fraction of it is discharging directly into the underside of Antarctica's most vulnerable grounding zones. The historical record confirms this systemic shift. While thermal expansion accounted for roughly 43% of global sea level rise over the last 60 years, the entire budget shifted in the 1990s, when land-based ice melt accelerated to become the primary driver of global ocean displacement. For decades, the subglacial topography of Antarctica was an unknown frontier. That data deficit was eliminated by the release of the Bedmap 3 project, a monumental compilation combining every geophysical dataset recorded since the 1950s, reinforced by 84 new airborne radar surveys from 15 separate international providers. This massive computational effort injected 52 million new measurement points and 1.9 million line kilometers of radar data into a single high-resolution structural map. Bedmap 3 revealed a total volume of 27 million cubic kilometers of ice, with depths reaching up to 4.8 kilometers. More critically, it exposed a fundamental structural division: the existence of two distinct Antarcticas. While East Antarctica rests safely on bedrock positioned above current sea levels, large sectors of West Antarctica are anchored deep within sub-sea level basins. Thwaites occupies the deepest and most unstable of these troughs, creating a perfect geometric conduit that invites warm ocean currents deep into the interior of the continental ice sheet. This structural vulnerability is further illuminated by the Polar RS climate dataset, which coordinates 4 advanced regional climate models at an 11-kilometer resolution to map the coastal weather dynamics of the continent. The deployment of these high-precision diagnostic tools was expected to reduce scientific uncertainty and potentially lower the estimated risk. Instead, every advancement in measurement resolution has revealed deeper subsea basins and more intricate pathways for ocean intrusion than anyone had previously mapped. The clearer our instruments see the system, the more dangerous the structural design appears. This realization shifts the investigation entirely. Thwaites is no longer analyzed as an isolated volatile glacier. It is recognized as the structural keystone of an entire marine ice sheet system. The glacier occupies a critical geographic choke point, physically bracing all the adjacent ice streams that drain the vast Amundsen Sea sector of West Antarctica. If this single keystone undergoes a full retreat, it stops supporting the surrounding ice systems. The removal of a keystone does not compromise a single stone. It causes the entire structural arch to collapse. Without the Thwaites barrier, the surrounding glacial systems, including the Pine Island Glacier, already recognized as one of the fastest changing ice features on the planet, lose their downstream restraint. The gatekeeper steps aside, allowing enormous volumes of inland ice to initiate a simultaneous, unhindered migration toward the marine basin, with no larger structural barrier remaining to intercept them. The physical mechanism that governs this runaway process is known as marine ice sheet instability, because the bedrock beneath the glacier slopes downward as it moves further inland. The grounding line, the exact boundary where the solid ice mass lifts off the seafloor and begins to float, is forced to retreat into progressively deeper water. Basic glaciological mechanics dictate that thicker ice at the grounding line discharges mass into the ocean at a much faster rate. This accelerated discharge forces the grounding line to pull back even further into the lower sections of the inland basin, where the ice is thicker still, driving the discharge rate exponentially higher. The process is a self-sustaining closed feedback loop. Once the threshold is crossed, the system lacks any internal mechanical brake to halt its own acceleration. The most advanced ice sheet models show that this destabilization is no longer a future projection. Thinning trends have already propagated roughly 100 kilometers inland along the glacier's main subsea trough, the exact structural signature of a marine ice sheet instability that has already initiated its opening phase in March of 2026. A critical modeling study led by Goldberg forced a confrontation with the true limits of our predictive systems. Researchers deployed 2 independent ice sheet models, rigorously calibrated against the documented real-world changes of the Thwaites system between 2004 and 2017, and ran the simulations forward to the year 2067. The results indicate that by the 2060s, Thwaites alone could reach an annual ice mass loss of 180 to 200 billion tons. This volume matches the total ice mass loss currently discharged by the entire Antarctic continent today. A single glacier is on track to match the output of an entire continent. But the most critical finding of the 2026 research strikes directly at the core of our scientific certainty. When the 2 independent models were evaluated, scientists discovered a deeply unsettling correlation: the specific models that matched the historical, observed data of the past 2 decades with the highest accuracy were the exact same models that projected the most extreme future ice losses. The high numbers cannot be dismissed as statistical anomalies or alarmist outliers. The scariest scenarios are being generated by the most accurate, well-calibrated instruments we possess. The tools earning the highest grades are the ones sounding the loudest alarm. When the independent methods agree on the trajectory, the conclusion is no longer background noise. It is a definitive physical signal. These models are not debating whether the mass loss will occur. They are merely refining the final scale of the calculation. This brings the structural analysis to its ultimate metric, the exact volume of water heading toward the global coastline. The Thwaites Glacier contains an internal ice volume sufficient to raise the global sea level by approximately 65 centimeters, more than 2 feet, acting entirely on its own. Such a rise would immediately redraw the flood maps and structural boundaries of every coastal zone on Earth. But because Thwaites functions as the regional keystone, its total removal unbuckles the wider West Antarctic ice sheet resting behind it. That larger ice mass contains a potential sea level equivalent of roughly 3 meters. 3 meters of global ocean expansion is close to 10 vertical feet of water added to every shoreline on the planet. This metric represents the displacement of between 500 million and 1 billion people worldwide, depending entirely on the speed at which civilization can construct artificial coastal defenses. The geography of this threat is immediate. It includes low-lying delta nations like Bangladesh, where tens of millions live within a few feet of the current high tide line, and it encompasses the primary economic engines of modern civilization: New York, Miami, London, Shanghai, and Tokyo. The baseline dynamics of the global ocean are already recording this acceleration. Through the latter half of the 20th century, global sea levels climbed at an average rate of roughly 2 millimeters per year. Between 2005 and 2023, that rate doubled to approximately 4 millimeters per year. The historical alibi that this acceleration represents a standard, long-term natural cycle is invalidated by the 20-year empirical record. The specific mechanism, warm, deep ocean water intruding into below-sea level basins, driving a documented 20-year acceleration of internal shear fractures, is the direct mechanical signature of an energy-loaded ocean, not a natural rhythm. The trajectory is locked on an upward acceleration. To maintain strict analytical precision, we must isolate the cartoon versions of this crisis from the hard physics of the system. The total collapse of the Thwaites Glacier will not occur next week. An ice mass of this magnitude possesses immense physical inertia and will unfold across decades and centuries. The coastlines will not drown by next month. The crisis that is genuinely imminent is the destruction of the floating shelf, the extraction of the mechanical cork from the bottle. What follows is the irreversible acceleration of the grounded glacier behind it. The studies documenting this process are openly published across major peer-reviewed journals, yet the reality remains obscured because a slow-moving, multi-decade structural failure lacks the immediate, single-frame shock value demanded by modern news cycles. The threat is driven by diffuse, macro-oceanic warming, a planetary force orders of magnitude beyond any localized phenomenon or artificial intervention. The critical marker to watch for right now is the official announcement that the Thwaites Eastern Ice Shelf has completely severed its connection to the main glacier. 4 separate, independent lines of evidence published within a single calendar window now converge on this identical conclusion. The Bedmap 3 terrain data confirms the subsea pathways letting the warm water in. The 20-year shear zone study records the structural slide toward failure. The global sea level budget proves that land ice melt has assumed control of ocean acceleration. And the calibrated ice sheet models warn that our most accurate predictive tools are the ones flashing the darkest forecasts. No single data point tells the story. Together, they form an empirical architecture that grows clearer and more severe with every observation. The ice sheet at the bottom of the planet appears isolated by distance, but the global ocean connects that fracturing single pinning point directly to the edge of every coastal city. The structural failure of the break has begun, raising a definitive systemic question. Once the keystone is removed from the West Antarctic ice sheet, what physical mechanism remains to prevent the entire arch from coming down? The physical reality of the post-shelf environment forces a direct confrontation with the laws of fluid dynamics and gravitational acceleration. To accurately chart the cascading consequences of the Thwaites transition, the analysis must move downstream from the macrostructural geology directly to the specific mechanics of the ice itself. When the Thwaites Eastern Ice Shelf shatters, it sets in motion a sequence of physical interconnections that transforms the internal geometry of the entire Amundsen Sea sector. The immediate consequence is not an instantaneous rise in water levels, but the total removal of the mechanical buttress. Without this 350-meter-thick slab providing continuous counterpressure, the friction at the grounding line is drastically altered. The inland ice, which measures up to 2 kilometers in thickness, experiences an immediate shift in its force balance. Gravitational pull driving the mass toward the ocean basin is no longer offset by the resistance of the pinning point. This triggers a geometric acceleration that propagates deep into the interior of the continent. As the ice at the marine front begins to discharge at a faster rate, it draws down the thickness of the glacier immediately behind it. This thinning signal does not remain localized at the coast. The 2026 data shows that this structural thinning has already traveled roughly 100 kilometers inland along the main subglacial trough. This is the physical signature of the marine ice sheet instability turning over in real time. The process operates on an unyielding mechanical feedback loop. As the grounding line is forced back by the melting action of the deep, warm ocean currents, it retreats down a reverse-sloping bedrock that dips further below sea level. The further the grounding line retreats, the thicker the ice face exposed to the water becomes. Because thicker ice discharges mass exponentially faster, the line is driven back even deeper into the basin. The system effectively begins to feed on its own mass, accelerating its output without requiring any increase in external atmospheric forcing. This macro collapse directly unbuckles the adjacent glacial systems that rely on Thwaites as their geographic gatekeeper. The Pine Island Glacier, already documented as one of the fastest-changing ice masses on the planet, shares this unstable subsea basin architecture. When the Thwaites keystone undergoes a full retreat, the structural arch of the entire Amundsen Sea sector is compromised. The neighboring glaciers lose their downstream restraint and begin a simultaneous migration toward the same marine outlet. There is no larger topographic feature or downstream structure remaining to catch or stabilize this accelerating mass. The entire West Antarctic ice sheet, containing a potential sea level equivalent of roughly 3 meters, becomes structurally unlocked at the microcomponent level. This massive displacement is driven by the precise thermodynamics of ocean stratification. A persistent superficial myth suggests that the melting of Antarctica is dictated by warming air temperatures or seasonal atmospheric cycles. The physics of the system completely deconstructs this interpretation. The destructive energy is delivered by a specific layer of relatively warm, salty water that travels far beneath the cold surface layer of the Southern Ocean. Moving along the deep trenches of the seafloor, this warm current directly penetrates the subglacial bedisons carved deep below sea level. The structural integrity of the glacier is being systematically eroded from below. At the exact grounding zones where the ice mass grips the bedrock anchors, this subsurface thermal attack is the direct consequence of a global planetary energy imbalance. The Earth's oceans cover more than 70% of the planet's surface and act as the primary thermal sink for the Earth system, absorbing approximately 90% of the excess heat trapped by greenhouse gases. This accumulated energy budget is not static. It circulates through deep ocean currents until it discharges against the most vulnerable ice foundations of the planet. The absolute scale of this energy transfer renders any alternative narratives of localized weather anomalies or artificial technology completely impossible. The physical force required to melt the underwater grounding zones of a glacier the size of Florida is orders of magnitude beyond any localized phenomenon. It is the manifestation of a diffuse, planet-wide thermal overload. This systemic crisis eventually converges on the human factor, translating abstract geophysical metrics into direct socioeconomic disruption. The global sea level budget confirms that the baseline dynamics have fundamentally broken away from historical norms. The rate of global sea level rise averaged roughly 2 millimeters per year since 1960, but between 2005 and 2023, that metric nearly doubled to approximately 4 millimeters per year, driven primarily by the acceleration of land-based ice melt. The total potential mass discharge from the Thwaites system alone represents a 65-centimeter increase in global sea level. While the wider West Antarctic collapse threatens a total rise of roughly 3 meters, this vertical expansion of the global ocean directly intersects with human geography. A 3-meter rise adds 10 feet of water to every shoreline on Earth, permanently altering the boundaries of human civilization. Coastal research indicates this displacement will directly impact between 500 million and 1 billion people. The structural load of this crisis falls heavily on low-lying delta populations, such as Bangladesh, where tens of millions of individuals reside within a few feet of the current high tide line. Simultaneously, it threatens the foundational infrastructure of the world's primary economic and cultural capitals, including New York, Miami, London, Shanghai, and Tokyo. The long-term trajectory of the global coastline is now explicitly tied to the internal shear fractures of a single ice shelf, demonstrating that an anomaly at the microscale of an Antarctic pinning point dictates the structural limits and survival parameters of human habitability across the globe. The validation of this planetary crisis rests upon the exact calibration of the diagnostic instruments deployed across the Antarctic continent. To understand how our predictive systems achieved this level of precision, the analysis must deconstruct the empirical data frameworks that eliminated decades of scientific uncertainty. For generations, the terrain hidden beneath kilometers of ice was one of the least understood surfaces on Earth, allowing superficial interpretations to obscure the true vulnerability of the ice sheet. This analytical blind spot was permanently dismantled by the publication of the Bedmap 3 project, a monumental structural map of the Antarctic bedrock. This dataset represents the synthesis of every geophysical record gathered since the 1950s, reinforced by 84 new airborne radar surveys executed by 15 separate international providers. This massive coordination injected 52 million new measurement points and approximately 1.9 million line kilometers of radar data into a single computational architecture, tracing the topography with an average resolution that narrows the distance between any mapped point and a physical measurement down to just 5.6 kilometers. The structural revelation of Bedmap Mat 3 completely reframes the global threat by exposing a mental geographic division, the existence of two distinct Antarcticas. While the massive East Antarctic ice sheet rests on solid bedrock positioned safely above sea level, the West Antarctic ice sheet is anchored inside deep geological basins that plunge far below the surface of the ocean. Thwaites Glacier sits directly within the deepest and most precarious of these marine troughs. This geometric configuration acts as a perfect subterranean conduit, inviting the dense, warm, salty currents of the deep ocean straight into the interior foundations of the ice sheet. Complementing this structural map is the Polar RES climate dataset, which integrates 4 state-of-the-art regional climate models at an 11-kilometer resolutions specifically tuned to capture the volatile coastal weather dynamics of the continent. Historically, the introduction of sharper instruments was expected to shrink uncertainty and perhaps reveal a more stable system. Instead, every advancement in diagnostic resolution has mapped deeper subsea basins and more intricate pathways for oceanic intrusion than anyone had previously anticipated. The clearer the view has gotten, the more dangerous the structural setup has proved to be. This high-resolution framework directly underpins the ice sheet models that project the future mass budget of the glacier. In a critical evaluation, researchers led by Goldberg deployed 2 independent ice sheet models, rigorously calibrated against the documented real-world changes of the Thwaites system between 2004 and 2017, and simulated the glacier's trajectory forward to the year 2067. The models converge on a stark systemic transition. By the 2060s, Thwaites is projected to reach annual ice losses of roughly 180 to 200 billion tons per year. This volume matches the total mass loss currently discharged by the entire Antarctic continent today, meaning a single glacial choke point is on track to match the output of an entire continent. The most unsettling aspect of this research strikes at the core of standard scientific caution. When the independent models were graded against 2 decades of hard physical observation, scientists discovered that the specific models matching the historical record with the highest fidelity were the exact same models that projected the largest future ice losses. The high numbers cannot be waved away as alarmist outliers or noise. They are generated by the most accurate, well-calibrated tools we possess. This empirical convergence effectively dismantles the tired public myths that models are inherently unreliable or that scientists are merely crying wolf. These separate modeling systems, built on entirely different methodology but graded against the same real-world observations, do not disagree on the direction of travel or the fundamental mechanics of the crisis. They differ slightly on the exact size of the mass loss, not on whether the loss is coming. This unyielding physical signal translates directly into the final structural limit of our global coastlines, where a full Thwaites retreat will unleash enough ice to raise global sea levels by 65 centimeters. While the subsequent unbuckling of the wider West Antarctic ice sheet threatens a total expansion of roughly 3 meters. This 10-foot vertical addition to the global ocean defines the ultimate human factor of the crisis, forcing a choice between an orderly trillions of dollars retreat behind artificial seawalls or a chaotic displacement of up to 1 billion people. The structural failure of the final pinning point is no longer an isolated geophysic event at the bottom of the world. It is the starting gun for a multi-century reconfiguration of the Earth system that cannot be deactivated once the keystone is removed. The final integration of the empirical data forces a definitive transition from diagnostic mapping to systemic prognosis. At this stage of structural degradation, the timeline of the Earth system can no longer be evaluated through superficial narratives of sudden, catastrophic world-ending events occurring next week. The hard physics of the Thwaites Glacier dictate a reality that operates on immense physical inertia, where a body of ice measuring 2 kilometers thick and spanning the size of an entire country cannot empty into the marine basin overnight. Anyone projecting an instantaneous drowning of global coastlines by next month is presenting a cartoon that actively undermines public understanding, making it easier to dismiss the verified threat as mere hyperbole. The physical reality documented across decades of research is far more calculated. The imminent event is the complete shattering of the floating shelf, an immediate mechanical failure that officially removes the break from the most dangerous glacial system on Earth. What follows over the subsequent years and decades is the irreversible, self-sustaining acceleration of the land-based mass behind it. This clear distinction between immediate structural failure and long-term mass acceleration effectively deconstructs the conspiratorial myths suggesting that the melting of the Antarctic sea sheet is being deliberately concealed or driven by artificial weather modification technologies. The data debunking these assertions is openly available, published across major peer-reviewed scientific journals for anyone to analyze. The absence of this crisis from daily front-page media is not evidence of a cover-up, but rather a structural feature of modern news cycles, which consistently prioritize fast-moving, short-term spectacles over multi-decade geophysical transformations. Furthermore, the claim of an engineered or artificial melt completely collapses when evaluated against the planetary energy budget. The thermal destruction of the sub-glacial anchors is driven by global oceans that cover more than 70% of the Earth's surface and have absorbed roughly 90% of the excess heat trapped within the entire Earth system. The physical force generated by this diffuse oceanic warming is orders of magnitude beyond the capacity of any localized machinery or intentional switch. It is the systemic expression of a planet-wide thermodynamic imbalance. The structural analysis thus converges on a single unmistakable signal that requires immediate global attention: the imminent announcement that the Thwaites Eastern Ice Shelf has completely severed its connection to the grounded glacier. This anticipated event will not raise the global sea level by a single inch on the afternoon it occurs, yet it marks the exact boundary where the mechanical constraint is permanently lost. 4 independent lines of evidence published within a tight calendar window now lock this conclusion into place. The Bedmap 3 terrain matrix exposes the exact subsea conduits that allow warm, salty currents to infiltrate the interior. The 2-decade fracture study documents the systematic failure of the shear zone. The global sea level record confirms that melting land-based ice has accelerated past thermal expansion to become the primary driver of ocean displacement, and the calibrated ice sheet models demonstrate that are most reliable. Observationally accurate predictive tools are the ones generating the most severe forecasts of future mass loss. No single line of evidence operates in isolation. Together, they form a unified empirical architecture where every new measurement sharpens the picture and confirms the severity of the setup. While the physical fracturing of this single submarine pinning point occurs in a remote geographic sector that feels impossibly distant from daily human life, the global ocean serves as a direct, unyielding physical connection that transmits the energy of that collapse straight to the edge of every coastal civilization. The acceleration of the global sea level from 2 millimeters to 4 millimeters per year is the measurable evidence that this process has already initiated its opening phase. The internal structural failure of the Antarctic break is complete, leaving modern civilization to confront the absolute limits of its coastal infrastructure as the removal of the regional keystone sets a multi-century planetary reconfiguration into unhindered motion. The structural deconstruction of the Thwaites Glacier system reaches its ultimate diagnostic boundary at the interface where empirical observations meet long-term global limits. To finalize this systemic investigation, the analysis must trace the final link in the chain of physical interconnections, mapping exactly how a microscopic crack in an Antarctic shear zone dictates the structural thresholds of human engineering. The foundational physics detailed across all 4 lines of evidence confirm that the planetary system has crossed a definitive point of inversion. When the Thwaites Eastern Ice Shelf experiences its final mechanical detachment, the event establishes what glaciologists classify as a largely committed sea level rise. This terminology represents a sobering physical law because of the massive thermal inertia of the global oceans and the slow grinding physics of continental ice sheets. The acceleration of the glacier becomes locked into the Earth system for centuries to come, completely independent of any future shifts in atmospheric composition or human carbon budgets. This baseline reality permanently invalidates the superficial myth that the crisis can be mitigated by rapid, short-term interventions or that the ice sheet will naturally stabilize once local temperatures fluctuate. The energy budget driving this transformation is already distributed deep within the marine architecture, having absorbed approximately 90% of the excess heat trapped across more than 70% of the planet's surface. The global ocean acts as a massive thermal battery that continuously discharges its stored energy directly into the subglacial basins mapped by Bedmap 3. The physical laws of thermal conduction ensure that this deep, salty water will continue to dissolve the underwater grounding lines from below, regardless of superficial atmospheric conditions. The historical data explicitly shows this structural handover. The accelerating rise of the oceans is no longer dominated by simple thermal expansion, which accounted for 43% of the rise over the past 60 years. Since the 1990s, the primary driver has structurally shifted to the direct melting of land-based ice masses, led by the systematic degradation of these very West Antarctic marine basins. This brings the systemic analysis to its final, unyielding human conclusion. The total potential mass discharge from the Thwaites Glacier alone holds enough internal volume to raise the global ocean by 65 centimeters, a metric that immediately redrafts the structural boundaries of every coastal city. Yet because Thwaites functions as the regional keystone, its removal unlocks the adjacent ice streams of the Amundsen Sea sector, including the volatile Pine Island Glacier. Without this single gatekeeper, the wider West Antarctic ice sheet faces an unhindered migration toward the sea, carrying a potential sea level equivalent of roughly 3 meters. This 10-foot vertical expansion represents the hard boundary where global coastal infrastructure meets its absolute structural limit. The data indicates that this scale of displacement directly threatens between 500 million and 1 billion people worldwide, permanently submerging low-lying delta nations like Bangladesh and breaching the artificial seawalls of the primary financial and cultural centers of modern civilization, from New York and Miami to London, Shanghai, and Tokyo. The acceleration of the global sea level rise from 2 millimeters to nearly 4 millimeters per year is the mathematical confirmation that the gears of this machine are already moving at an accelerated pace. The structural failure of the single pinning point is not an isolated prophecy for the end of the century. It is an active physical reality currently unfolding within our own calendar. The independent models calibrated by researchers like Goldberg demonstrate with rigorous accuracy that the most reliable, historically verified instruments are the exact ones projecting the most severe future mass losses, indicating that the high-end scenarios are the closest representation of our physical future. Ultimately, the system reveals a rigid, calculated architecture of loads and structural limits. Antarctica is not an isolated wilderness detached from human geography. It is the physical anchor of the modern global coastline. The removal of the mechanical break from the widest glacier on Earth marks the definitive conclusion of a stable planetary epoch, leaving civilization to adapt to an encroaching global ocean that is rising not by a temporary natural rhythm, but by the unyielding mechanics of a structurally overloaded planet.